Okay, so welcome back again, and this is the Chipmaster, and in this video I will be repairing another MacBook, which is the same model that I repaired in the last video, which wasn't detecting the SSD drives. And this one that I got now from a tech yesterday, she told me that it's not turning on, and it's written on it, right? So MacBook Pro 2017 not powering on, right? Suspect logic board, as you can see, right? So that's what they told me, and that's what is written on it, right? I don't know what's wrong with it. I just got it yesterday, so I'm going to repair it. I hope this MacBook, this has a problem, sorry, with a signature problem where a capacitor that's normally shorted on the one of the power delivery chips under a metal, I think it's beside the Thunderbolt chip there, under the shield. There's a cap there that's normally cracked, which always causing the short and causing it not to boost, and hence can't turn on. Alright, so I'm gonna plug in the power supply now. Alright, so let's take a look at the USB-C meter. Alright, so I think, as you can see, I got 5 volts. It goes from 0 on the outside. The in is 20 volts, and if you take a look at the out, it goes to 0 then back to 5 volts, but I'm not getting the blue lights. I'm trying the next port, right? 0 to 5. It's not taking any current whatsoever. Right, I'm going on the other port. Right, it goes to 0, 5 volts, and it's taking some amp and then it goes away. Not taking any current whatsoever on the other port. Right, 0, 5 volts, nothing. So as you can see, all 4 ports, no blue lights, not boosting to 5 volts, not taking any current whatsoever. So I believe this is a definitely not turning on fault, no power. Right, so I will now head over. Alright, so let's do this. Oh, the screws are out already. Oh, there's one screw here, and that's a regular Phillips. So these are even the correct screws for the computer. Okay, well, it was checked by another technician, as I said before, so they couldn't repair it, they couldn't figure it out, so they sent it for me to repair it. The CPU is good. Yesterday I was doing a BJ repair on a HP, but I haven't fixed it as yet, so I'll need to check the LPC bus because it was a no display, and upon checking I wasn't getting any reading from the BIOS and the RAM, so I suspected the CPU was a problem, but I replaced the CPU, but it's still same phenomenon, same fault, so I will have to check that later on today while working. So the CPU is good. It's a Stony Ridge AMD CPU with a 2 GHz frequency speed. Alright. Alright, so as you all know, visual inspection as always. Alright, so I'm now looking. As you can see, the watermark indicator is intact. Right, so there's not any liquid into the computer. Other side, as you can see, also white and clean, so there's no liquid intake on this computer as yet. Okay, no liquid intake whatsoever. Alright, so I'm just examining on this side of the board for any liquid intake or any burn, any explosion that could lead to the suspect of the problem. Alright, so I haven't found any explosion, any liquid intake on any other area of the board, so it seems good. Alright, this was the exact model that I repaired in the last video that wasn't detecting the hard drive, and now this one is not turning on. Alright, so I'll continue the disassembly process. This flex, as I said before, is very thin, easily prone to tear. Right. Yeah, because the machine was already disassembled by another technician, so I always have to check if the fingerprint flex ribbon is torn or pinched. Alright. Okay. Alright, so taking out the board now. See, always forget the battery. I don't know when I'm going to stop. Always forgetting to disconnect the battery first. Oh boy. Alright, board is out. Alright, so I'm just gonna do some resistance check at the moment. Alright, so I'm checking first on PP bus. This fuse here is a PP bus. Alright, so this fuse here is for the PP bus. So I'm checking it now if there's a short there, and it's all clear, but there's no short there. So right here under this part here, I forgot to look at the dust. Look at the dust there. This is what I was talking about. So it's under the NAND, not the Thunderbolt chip. So you see this dust here? This dust is normally gathered after are accumulated over a period of time and causing this capacitor here to crack right here under the metal here that I was talking before. And this is a signature problem, as you can see. Right here is a circuit that I was repairing in the last video. As you can see, the exact rust is there, the exact debris. So as I was telling you, this is a common mistake. This is a very big mistake that Apple did in the engineering of the case. Right, the edges, right, of the board are always prone to dust. Here's the other side. Right, as you can see, there's dust. It's always prone to dust and liquid intake, and easily to gather mildew, right, on the power delivery chips. So this is a big manufacturer flaw. Right, so as you can see, the capacitor is normally cracked right under here. Right, see that sometimes we have to move this piece of metal, extra piece of metal here, and remove it out the way so we can access the capacitor. Right, so I'm just gonna dust off the board. Okay, let's take a look again. Right, and there's still some more dust in between here. As you can see, the capacitor is right under the metal here. Here it is, that cap. Always break. So let's check the resistance to ground on the other cap, which is for the PP3V3. Can use anyone because they're connected. Let me go over this side. If it's shorted, alright, that one's good. Here we go. So here's the short. Here's the short. Next side. So you see that cap. As you can see, I'm getting the short here. So that's a signature failure. It's a signature problem on these MacBooks. So basically, the laptop is repaired already, isn't it? So I'm just going to use just going to move this metal out the way. This piece of metal. Let me get this one. See if I can grab it. Alright, it's out the way now. Sometimes you can also see the crack. Let me see if I can pick it up on this camera. Alright, so that cap here, right under here, this is a signature failure. This is done many times on YouTube. This cap here, this one. So I don't even have to check, I'm just going to remove it with my tweezer. See if I can rock it out. There we go. So let me see if the short, so I just use my tweezer and break it out the circuit, as you can see. So it's now removed right here. I removed it. So I'm going to check now the resistance to ground on the other side of the chip that I've just checked, to see if the short is restored. The resistance is restored, I mean. Indeed. And it's fixed. And that's a signature problem, isn't it? Alright, so we're all clear. Let me just brush off this side because, as I said, the edges of the board are normally prone to dust and liquid intake. Just brushing it off. These are some of my fellow YouTuber Northridge favorite repairs of repairing capacitors. And these are the repairs that he likes. Anyway, so I'm going to put a cap there. Let me go under the microscope. I can't see. Alright, so going under the microscope now. Alright. Okay, so alright, so I want to put the cap there. So this capacitor here is normally used to power the BIOS chip, the ROM chip, as I said before. This ROM chip. This is the ROM chip. This is the ROM chip for the BIOS, for the PD, for the power delivery chip. This is the BIOS. Alright, so this chip, as I said before, will read this chip, right, and then it will configure the GPIO pins inside of the chip. Then it will now start to talk to the charger to learn the power capabilities of the charger, right? After learning the power capabilities of the charger, it will then send a request to the charger through packets, and I explained this in the last video. And each packet is sent. The charger will then now initiate the accept command and the power ready command and accept the request and start to initialize the proper voltage and current to send to the computer, right? And then now it will start boosting, and that's how the configuration channel works. All right, so I'm going to tin here with some solder if I can reach there. Let me get my smaller iron. Alright. Alright, so I'm now tinning. So this is a 0402 capacitor. Oh. We get a new 0402. Alright, so here's the new capacitor here. So just gonna add some flux into my tweezer to remove the capacitor. Okay. Alright, so you should always put back these capacitors. They are very important because this is a linear voltage, and if you remove the capacitor on a linear voltage line from the base of the origin of the generation, or where the voltage is generating, it will cause fluctuations and put the chip into under voltage or over voltage protection mode, because it cannot stabilize the voltage. So the help of the capacitor is used to help stabilize and to filter out the ripple or any unstable, which can be caused by any unstable fluctuation, or it can be caused by electromagnetic interference, or we can call it EMI. Alright, so it's very important to put back the capacitor at the root or the origin of where this voltage is generated. Alright, so I'm just making sure. I think I put too much solder there, so I will just use the iron here to remove the excess solder at the side here. There we go. Alright, so now clean the board. Alright, so going back to the multimeter, I'm going to connect the power supply. Adapter. Okay. just need one of them. Alright. So I'm going to connect. So I'm going to head over back to the power supply USB-C adapter to take a look at the current consumption, to see if it boosts and works. Okay. Alright, so make sure that I get a good focus. Now take a look at the side here. You should get the blue lights, right, and that indicate the BIOS is successfully read, and the protocol, communication protocol with the configuration channel is also good. Alright, so I'm going to plug in the charger now. Take a look. Alright, so it's 5 volts. We got the blue light immediately as I plug in the charger, and it's now boosted to 19 volts as you can see, and it's on. Alright, so it's all good. So in the last video I was supposed to demonstrate the working process of this power delivery chip with talking to the BIOS. So I'm going to demonstrate that now, and how many volt and which voltage you should check to know if the BIOS is working properly. So I'm gonna see if I can demonstrate doing that now. Okay, so let me get over to the oscilloscope for demonstration purpose. Alright. Accidentally remove the power from the oscilloscope there. Alright, here we go. Let's turn on the aperture some more. There. Now what I'm gonna connect the probes to the BIOS chip pin number 1. I think I'll have to go under the microscope for this one. Sorry about that. so I need to read the BIOS chip. So I need to put my focus on the BIOS chip here. Oh, it's on the other side. Alright, so we'll go back to picture-in-picture mode now. Alright, so we'll just alright, so remove the power. Alright, so I'm just connecting the oscilloscope. Alright, so we're going to take a look at the alright, so pin number 1. Capacitor should be, resistor should be here, I believe. Let me take a look. Let me check if it's in continuity first. Let me see now. Yes, that's the capacitor, that's the resistor. Alright, so I'm just gonna set up my oscilloscope now to capture this signal. Oh, it's already set up for the voltage for the signal. Alright, so that's 2 volts per division, 500 microseconds, and my trigger level is set to 900 millivolts, thereabout. So I'm going to connect my oscilloscope to the resistor there. Oh, I need to set my time base up some more. I'll set it to 10 milliseconds, and I will give power to the board. Let's go. I can't see. Alright. So as you can see, the BIOS is read by the power delivery chip there. Alright, let me go again. One more time. Here we go. See? Alright, let me go again. We can capture that one good, properly. Alright. Oh, there we go. Let me go again. One more time. There we go. As you can see, it's read. So it take approximately 200 milliseconds. So that's roughly 400 milliseconds it takes to read the BIOS. Right, so that's 400 milliseconds, and it will read immediately. So this after the reading of the BIOS, then let me head over to the schematic section. So I have the schematic here. I opened it already. So after the chip reads the BIOS through the SPI bus here, as you can see, it's grounded. So this chip is not reading the BIOS, so it has to go through this bus, which is the UART bus, as we all know it. So it stands for Universal Asynchronous Receiving and Transmitting of Information. So we have an in and an out, and this is a communication line between the two power delivery chips. Right, so this chip, as you can see, is grounded. Its SPI bus is connected to ground, so that indicates that this chip is not reading the BIOS. right? So the chip that's reading the BIOS, let's go to the board view. I'm on the other side, the NAND side. Here we are. So this is the BIOS chip, or the EEPROM chip for this chip, and that's UB400. And this is the BIOS. This is the chip select pins. As you can see, this chip is not reading the BIOS, right? So it's the other chip on the other side of the board here. As you can see, is reading the BIOS. So this chip has to go through UB300 in order to read its BIOS through the UART bus. And let's see if I can find it over here. I think I passed it already. UPC. Yes, here it is. So that's the receiving. Sorry, that's transmitting. So it's pin 36. As you can see, it's connected with the other chip here. As you can see, it goes through. So if this resistor is broken, then definitely it cannot communicate. Then it will stop. No boost. It will stop at stuck at 5 volts only, and hence you can't get the laptop to turn on. So as you can see, this chip is not reading the BIOS. So this chip, in order for it to read the BIOS, if you plug in the charger on this port controller for this power delivery chip, then it will need to go through the UART bus to read the BIOS, right? So as you can see, it's grounded. So UB400, UB3100, so it's not reading the BIOS. Oh, sorry, so it's UB3100. Let me go to UB300. So let's check the SPI pins for it. As you can see now, we have some signals. So this indicates that this is the master chip. So master out, slave in, master in, slave out. So this chip is actually reading its BIOS. So this is the master chip because it needs to go through the chip select pin. Let me get my marker. Okay, so as you can see, this chip is going out to read a BIOS. As you can see, this is the pin, right? Chip select. This is the key signal that I was checking a while ago. So this is the signal that I checked with the oscilloscope, right? And it's going out to read its EEPROM chip, and then it will configure its rest of GPIO pins. These are the GPIO pins, right? See? So we have UPC. This is for debug, the UART, right? And these GPIO pins must be configured. So in order for this pin to function, it must read this pin, which is the chip select pin, and then these pins will start to communicate with the EEPROM chip. Once the program inside of the EEPROM chip is okay, then it will start to configure these pins. So which pin is going to act as an in, which pin is going to act as an out, because this chip can be installed on another laptop. It can be installed on most Dells. Most Dells use the TPS series. You can install this chip and program it to work on a Dell, right? If it is compatible with the BGA package, right? So that is why these chips need to read an EEPROM chip, because they are manufactured and they can be used on other devices, right? So that is why you need a GPIO pin. So GPIO stands for General Purpose Input Output. So this is a 0 order, so from 0 to 8, right? So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, and these pins are needed in order for it to work, right? So those are the GPIO pins that is necessary for it to work. So after the BIOS is read, then this will release a 1.1 volt LDO right here, which is the BMC pin here, this pin. After the BIOS is read, you will get a voltage here. If the BIOS is not read, then you won't get this 1.1 voltage, right? Very important. So most time this voltage is used as a reference. See, it goes nowhere, so it's just a reference, right? So this is just a reference. If you want to know if the BIOS is okay, you can simply check here pin number. This is the E1 pin, and this pin is connected to this capacitor CB304, which is a 2.2 microfarad capacitor, 4 volts, right? 0201 in size, and you can check here. right? So let me check. So I'm going back over to the microscope. Turn up by the aperture and focus. Alright, so I'm gonna check on that pin and that CB304. So I'm just gonna check and confirm its location. CB304. 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 Alright, and that's on the other side. Just getting the alright. So CB304 is on the target on the side that I've just repaired. So it's right here. So this is CB304 right here. It has some glue around it. So this is CB304, right, and that's 1.1 volts there. So I'm gonna give power. Right, so I should get 1.1 volts here. Don't tell me that I'm on AC. Oh god. Alright, so I had to scrape a little bit more to get to the cap. So I'm gonna check now. Here is it. Here's the 1 volt. Alright, so that's the 1 volt. So each chip, each connector, each port you plug it in, that chip will deliver that 1.1 volts. Right? So when I check the other chip, it's not generated. But on this chip that I plug the port in, it's generated. So that's the 1.1 volt. So if the BIOS is not reading, you won't get this 1.1 volt regardless. Right? So if I remove the BIOS chip, the board will be completely dead. We won't get 1.1 volt. Right? So this 1 volt is the reference to indicate that the BIOS is okay and intact, and the chip is okay and intact as well. So if I remove the BIOS, then it won't work. Okay, so I'm going to remove the BIOS. I'm going to move the RAM chip. I always call it the BIOS. So I will remove a RAM chip. So the RAM chip is going to be removed now. Alright, RAM chip is removed. And I'm going back to this to check again. Okay. Alright, so as you can see, I'm taking the 5 volts, not boosting, no blue lights. And no voltage, as you can see. There's no voltage here. Alright. Trying the other port. Check in. No voltage. See? So if the BIOS is not reading, you won't get this 1.1 voltage. So if you want to quick identify your fault, you check here. So if you're getting 3.3 volts coming out of the chip, as you can see, 3.3 volts is coming out of the chip, right? I'm getting 3.3 volts here as well, right? This should be 5 volts right here, right? That's because I'm not plugging in the other port. So if I plug it in the other port, the 5 volts will be coming here. Oh, yes. Hold on, let me check. Sensing. Yes. Okay, so here's the 5 volts, as you can see. Right, so the 5 volt is there. So it's input. I'm getting 3.3 volts here, 3.4 volts. The capacitor that I've just replaced, this is a PP3V3 underscore D3, right? And this is PP3V3 underscore LDO, but I'm not getting the 1.1 volt here because the BIOS strip is removed. So I'm going to solder back the BIOS. So that 1.1 volt is a reference voltage and it is operated inside of the chip, right, for internal purpose, but it's outputting to that capacitor as a reference. So please bear that in mind. I'm just doing this ready. Alright, so I'll now solder about the BIOS ROM chip, or the ROM chip for the chip. I'll go into the light. Alright, so I'm soldering back the chip now. Alright. Moving these small solder blobs here. There we go. And now let me clean with some 99.9. Right, so I'm gonna connect back the power now. Going back to the spot that I was before. Alright, so I'm plugging in the power now. Alright, so I get the blue lights. Everything is working. Let's see if we're getting back that 1.1 volt. Let me try the other port. There we go. So we get the 1.1 volt back. So as you can see, after the BIOS is read, the 1.1 volt will be generated, right? So if the 1.1 volt is not generated, then you should check 3.3 volts here, this 3.3 volts here, right? And then now you should be able, and if you not get it, then you check the working conditions of the BIOS. There's something wrong with the BIOS software or the BIOS not getting any power. Alright, so that's how it is. That's the process in which the power delivery chip is producing and operation of that voltage during the working sequence. Right, so that's how the power delivery chips work with the BIOS on these Apple. all the Apple MacBooks from the T1, this is a T1 base, all the way up to the Silicon M1, right? And that's how that architecture was developed and designed, right? So I'm going to put this unit back together. I'm going to pause the video because I'm way over 55 minutes now in this video. So I'm going to put it back together and then get back to you to see the results. Okay, and now for the final test. Alright, so I will now connect the adapter. Alright, it's on. Alright, there we go. As you can see the progress bar. Just checking to see if the fan was spinning fast. There we have the mouse. And there we go. Alright, so it's up and running. Alright, so I hope you enjoyed the video and I hope you learned something. Alright, that part there when the BIOS, the EEPROM chip is not read properly. And understanding how the Type-C power delivery works for the Apple, where the BIOS and that 1.1 volt that is produced after reading the BIOS. If the BIOS is not read, it can't produce that 1.1 volt because that voltage is operated internally, right, for reference, and it is outputted for reference to check that capacitor, but it's operated internally only for the chip, and it only is going to be generated on the corresponding port. So if you plug it on one port, then you won't get that voltage on the other ports, on the other power delivery chips, right? So it only be going to be generated based on the current port that is plugged in, right? So that 1.1 volt is the key for checking if the BIOS is corrupt or the working conditions of the BIOS and the power delivery chip is not working or a missing condition. Alright, so I hope you learned something. Alright, so I hope you enjoyed the video, and in the next video again I will fix something for you, okay? Alright, bye.